The common understanding is that GPS and GNSS in general does not work, or at least does not work well indoors, and so cannot be used for timing purposes indoors either. This idea has pushed PTP and DTP, which is PTP over DOCSIS for the cable systems, to the limits of their capability and perhaps other ideas as well. I'm going to present a new technology that overturns this idea and shows that GPS can indeed be used to provide timing and location even deep indoors. This rather wordy slide compares the various GPS receiver systems generally in use today. Interestingly, a chicken or the egg situation exists with all GPS. It works best if it already knows the time and its location. This is actually part of the idea behind assisted GPS. Plain, unassisted GPS receivers get some very coarse location and time information from the satellites themselves, and so eventually will converge. Once a location is calculated, they use this as the a priori known location to help kickstart the search process for subsequent startups. These receivers trade off sensitivity for acquisition speed, which was the intention of GPS system design, as it basically is a line of sight system. GPS can provide time indoors, but it requires an antenna usually on the rooftop, in some cases near a window, and distributes time through indoor cabling, either RF or Ethernet. The outdoor antenna installations can be costly due to insurance, leasing, and installation. Cellular assisted GPS gets fairly good initial time and location assistance from the cellular network and works well outdoors, but is much less reliable indoors. Also, its acquisition sensitivity is not as good as its tracking sensitivity and further limits indoor performance. Internet-assisted GPS exists today and is similar to cellular-assisted, but the technology presented here is a greatly enhanced Internet-assisted system. This method provides more assistance data, which I will describe. It also has basically the same sensitivity and tracking as acquisition, since in its purest form, tracking does not exist. So what does the system architecture look like? This is a high-level block diagram of the Enhanced Assisted Internet GPS system. At the top right is depicted an unassisted GPS reference receiver, of which only about 5 are needed to cover the entire U.S. These receivers have antennas positioned above the local structures and have visibility to all the satellites radiating in the area, typically about 12. Their role is to monitor each satellite vehicle, or SV, and read its ephemeris data, as well as record the 50 bit per second data modulated on each SV's unique PRN CDMA code and distribute it to the clients typically over the internet, but it can also be over Wi-Fi or cellular. It also measures the actual SV power on the ground for path loss calculations, but is not used for timing. The second block down is basically a PTP grandmaster, which distributes time over the internet for initial synchronization. Last in line is the cloud server, which is used to provide high computational power when called for, typically for the first acquisition. At the left is an embedded GPS snapshot receiver with a local or embedded GPS antenna positioned somewhat arbitrarily and conveniently indoors, which uses the traditional distance data, the 50 bit per second data, and other data. The IQ samples collected by the receiver are routed to the cloud processor, and by using a combination of coherent and non-coherent integrations, achieves the extreme sensitivity of minus 175 dBm. This provides 50 dB margin over the line-of-sight GPS signal level and enables indoor operation. I am sure the use of PTP has drawn some attention and will be discussed next. PTP with a remote grandmaster delivered over the internet with and without PTP-aware networks has been tried in an attempt to deliver 3GPP timing accuracy to the required 1.5 microseconds, but these have not been widely deployed or even deployed at all. Some have deployed unassisted GPS receivers with an antenna on the building rooftop with indoor grandmasters and time distributed indoors with PTP. This comes with all the complications stated earlier. One small cell vendor even told us that installation is the customer's problem. This new technology uses PTP unaware networks to deliver course time and frequency to the software-defined radio from a remote grandmaster as seen earlier. In this case, the PTP session is only used to prime the pulse per second to limit the time search range of the SDR, and also to prime the TCXO frequency and pulse per second rate, which is slave to the TCXO. The PTP session can be as short as 30 seconds using innovative PTP code that is designed for optimum rapid acquisition. This new technology uses SDR in the cloud and in some cases can be computed in the local client. With SDR cloud computing, PTP time errors of up to 5 milliseconds and even larger are possible to prime the GPS receiver. Thus, a short PTP session over unaware networks is adequate. Enhanced Internet-Assisted GPS acquires GPS signals in one long integration snapshot GPS measurement, and so the name adopted. After a successful GPS acquisition, PTP is disengaged and GPS time tracking and TCXO frequency maintenance is kept locally in the client derived from GPS requiring low computation capability. So how does the receiver develop its extreme sensitivity? Earlier I mentioned we use a combination of coherent integration, where the signal phase is kept, and non-coherent, where the signal phase is removed. Coherent integration is used first since it provides linear gain versus the coherent integration length as seen in the top right figure. This is used until the TCXO Allen variant starts degrading the detection. Typically 1 second or more can be used, but it depends on the TCXO deployed. Then non-coherent integration is used again until detection is degraded, typically after 300 to 400 seconds using a femtocell TCXO, but this can vary widely depending on the oscillator. The gain is nonlinear with the number of coherent integrations as seen in the bottom right. And at 300 NCIs, the gain is 17 dB versus 25 dB if it were linear. The lesson is increase the coherent integration until Allen variant starts degrading performance. Then switch to non-coherent integration, increasing those until the linearity is intolerable or the Allen variant limits performance. This slide describes the processes in a little more detail. Earlier I pointed out that each SV's 50 bit per second data is delivered as part of the assistance data. It is important to note that the 50 bit per second data modulated on the GPS PRN code, depicted and not to scale as the red chips, is removed from the input signal by generating a replica of the expected GPS PRN code plus the 50 bit per second received as assistance data. Here we can identify the coherent and non-coherent integration processes, where the non-coherent integration is a summation of the essentially squared coherent integration intervals. All GPS receivers have the code replica, but with this technology, the 50 bit per second is delivered from the assistance network and aligns it with the PPS to remove it from the signal. A time alignment and frequency search through the correlation process is conducted over a range of pulse per second time offsets and frequencies, as the pulse per second is not perfect, as depicted in the lower right figure. This leads to a sensitivity of minus 175 dBm. Now we will get into how this technology performs. This slide depicts results from our first attempt to see how well the technology worked in practice. Our lab was initially located on the second floor of an engineering building at the University of Colorado. Once the receiver was working successfully on the second floor, we undertook an effort to find a location where it had difficulty. We kept moving the antenna deeper and lower into the building until we placed it in what is called the second basement, as the room above it is partially underground and it still worked well. This room is completely underground and has no windows. The patch antenna used for the GPS receiver is pointed out on a file cabinet. The bottom two traces on the right plot the horizontal and vertical location errors versus time in increments of 300-second measurements. The blue dots are the instantaneous GPS solutions using only the satellites acquired over that 300-second measurement interval. This is how a traditional GPS receiver works. It only uses the coincident satellite measurements, but they also have averaging techniques which smooth out the excursions but does not improve the accuracy. We have innovated this process to use many ESV measurements or pseudo-ranges non-coincident in time. This we call joint processing and is a form of time diversity and is seen as the green traces. This has an averaging effect, but is not averaging, and greatly expands the accuracy and stability of the system. Getting to the time, the GPS calculated time errors relative to an accurate rooftop GPS receiver pulse per second are seen in the upper right. These are not physical measurements since we did not have an actual pulse per second signal from our receiver at this early phase. The time error is a calculated time error for the enhanced internet-assisted GPS receiver versus the rooftop pulse per second. The accuracy is summarized below left as a 34 nanosecond RMS error and is a bit optimistic since it is virtual, but is indicative of performance. Also on the bottom left are the location errors for the last joint processing results of 24 meter horizontal and 1.6 meter vertical. A post-process solution, which is a proprietary process to find the optimum solution over all the data and can even compute days of measurements, improves the location errors to 19 meter horizontal and 0.5 meter vertical in this case. Next, we move to a measurement session we conducted in a customer building in Bundae, Korea. The green arrow points out the 8-story building we tested in, which is nestled in a group of similar and some higher buildings. We conducted tests in many locations in the building, but here we focus on the basement as seen in the lower left. The antenna, next to the receiver, is pointed out in this panoramic picture of the basement. You can see the underground parking garage on the right. The top right oscilloscope picture shows the typical pulse per second performance and is near zero with the reference in orange and the recovered in blue. The bottom right is a picture of a maximum time error of about 100 nanoseconds measured in this location. A customer recently conducted a long-term timekeeping test over a span of 7 days. They placed the receiver on the first floor in the center of the building and conducted a test over 1 week. A picture of the 2-story building is shown on the left. The test system measured the difference between a rooftop antenna GPS discipline rubidium oscillator generating a 1 pulse per second and the enhanced internet-assisted GPS receiver generated pulse per second. Here we see the stability of the timekeeping system. With a standard deviation of 84 nanoseconds and a peak error of 494 nanoseconds. The time recovery is still being optimized and enhancements are coming. In conclusion, we have shown that GPS using extensive internet assistance can work indoors. SDR provides a low-cost solution and can be extended to other GNSS systems. Thank you.